Welcome to our video. My name is Ladislav Gaál, representing the MicroStep-MIS company, and I am going to talk about precipitation nowcasting, where measured data are supplied by meteorological radars and architectures of AI are adopted to increase the performance of the rainfall nowcast. The target region is Central Europe, more specifically Slovakia and its close vicinity. This video was meant to present the essence and the results of the scientific project called Precise Thunderstorm Forecast in a Changing Climate with the acronym PRUDENCE. The scientific project was supported by the Slovak Research and Development Agency and was carried out in the period between 2023 and 2026. Both participating research teams are resided in Bratislava, Slovakia. These are the MicroStep-MIS company and the Slovak Hydrometeorological Institute. The list of the researchers who were involved is put here. In this video, I will try to talk about the basic goals of our project, to explain the concept of the adopted architecture. That means the difference between the so-called baseline models and the meta models, to describe the inputs and outputs, and more importantly, to present the performance of our newly developed nowcasting models. What are the project goals? The overall goal of the project was to increase the performance of thunderstorm forecast using some of the newest AI techniques, namely to maximize the thunderstorm detection capability and to minimize the number of false alarms. The first goal is linked with a high probability of detection, whereas the second is associated with low false alarm ratio. For instance, in the aviation sector, improved thunderstorm forecasting can support more informed operational decision-making, lower cost of preventive actions, and more efficient use of available capacity. Let us start with the input data. The radar observations come from the network of 4 meteorological radars operated by the Slovak Hydrometeorological Institute. Their location is visualized by the blue dots on the map, and the nominal range of radars are depicted by the blue circles. The target area for the analysis is highlighted by the red rectangle. All 4 radars belong to the category of C-band, that is, they operate at a wavelength of 5 centimeters. They perform volume scans every 5 minutes, and composite products are then automatically generated for each radar scan. From a temporal perspective, the radar data cover the warm half of the year, from April through September, and they were selected for the period of 2017 and 2023. We introduced this seasonal limitation since the study focuses on convective precipitation, storms and showers, which, under the climatic conditions of Central Europe, occur predominantly during this time of year. The radar data were then refined, and from the analysis we excluded days with a cloudless atmosphere, pixels with very low rainfall intensity, and radar composite areas with low rainfall coverage. We've got a 2-level concept of the AI-based nowcasting. On the first level, we use several nowcasting models. We call them baseline models. All of them provide some nowcast for the near future. The tricky point of our model is the fact that we build a meta model, which is a kind of an envelope to the baseline models. The second level meta model is embedded within the ensemble stacking approach. The role of this meta model is to select the best performing baseline model for each timestamp in the analyzed period and for each forecast lead time. Now we look at the individual parts of the scheme in more detail. We have chosen 6 different well-established optical flow models that are widely used in practice. 4 of these 6 models are also available within the PySteps library, which is a tool especially designed for radar-based nowcasting tasks. The individual baseline models reflect different concepts. Titan and DARTS are both an object-based radar nowcasting system where convective cells are identified using some predefined reflectivity thresholds. TREC represents field-based extrapolation, that is, estimates motion of the entire precipitation field. SPRO, spectral prognosis, represents a spectral extrapolation nowcasting technique that operates in Fourier space. STEPS is a stochastic ensemble nowcasting framework that builds upon spectral decomposition, and here it is implemented as a deterministic model that is the average of ensemble members. Finally, ANVIL is an autoregressive modeling of time series of the VIL product, that means the vertically integrated liquid radar product. The meta model is a superior one where the goal is to find the best of the 6 baseline models. How do we achieve this? We train the baseline models using a hindcast approach. This involves stepping back in time and generating nowcast predictions for each timestamp as if the future were unknown. However, because these forecasts are made for past events, the actual future is known, so we can assess the performance of each baseline model and identify the best performer for each timestamp and each lead time. For this purpose, we adopted 12 widely used evaluation metrics. The verification of the nowcasting is a standard procedure. It is based on the 2x2 contingency table, which evaluates the pixel-wise comparison of the predictions and the ground truth in terms of the true positives, false negatives, false positives, and true negatives. Such an analysis is then summed up through all pixels and all timestamps. In the table that we see here, we have 12 verification metrics that we use to evaluate the performance of our nowcasting models. Among them, there are both well-known metrics such as POD, FAR, CSI, or F1 score, and also some specific ones. The most important question, however, is how do we define the best baseline method in the training? We evaluate the performance of each baseline model by each of the 12 metrics. For a given timestamp and lead time, the best baseline is defined as the model that most frequently ranks at the first position across the 12 considered validation metrics. Let's go back to the schematic of the nowcasting model, and now let's focus on the core transformation function of the nowcasting architecture. Graphically, we can visualize the transformation function fx as follows. On the left-hand side, there is the input dataset X. It is multidimensional, consisting of a sequence of two-dimensional images representing radar-derived or other characteristics. In contrast, the left-hand side of the schematic represents a single-bit output that encodes the identifier of the best-performing baseline model. The task can be formulated as a classification problem, where the inputs are sequences of images and the outputs are sequences of discrete labels. This transformation function is a modification of the UNet convolutional neural network. Here, however, we do not use a decoder on the output. Instead, a simple linear transformation is applied to produce the output. We call this architecture as L-class for two reasons. The resulting architectural shape resembles the letter L, and the function solves a classification problem. We are back again at the schematic of the model. As soon as the L-class transformation function finds the index k, that is the best performing baseline model, It uses to derive the nowcast for the lead times ranging from 5 minutes to 60 minutes. Note that the meta model is configured the way that different baselines may be identified to produce nowcasts for different lead times. Now, there is one more issue we haven't talked about, and this is the left side of the schematic, the input data denoted as X. We adopted two basic radar products that are supposed to be as indicators of the possible future presence of thunderstorms. The first one is the vertically integrated liquid, abbreviated as VIL. This is the estimation of the total amount of liquid water in a vertical column in the atmosphere above a given location. The second is CAPPI, constant altitude plane position indicator. It is a horizontal slice through the radar volume data at a selected altitude above the Earth's surface, here at the level of 2 kilometers. The third input is not a radar product, however, it is closely associated with thunderstorms. These data are the information on the occurrence of lightning strikes obtained from the European LINET system. We use these three kinds of input data to train our different L-class models. Namely, our first model is purely based on the sequence of VIL fields. Our second L-class model takes CAPPI as data input. And last but not least, our third L-class model is also based on the CAPPI data, but it is extended with the information on lightning occurrence. Before we arrive at the evaluation of different nowcasting models, here are some additional information on the procedure of training and testing. The entire dataset was divided into two subparts, where 70% of the data was used to train the models, and the remaining 30% served for independent testing of their performance. Furthermore, the Optuna framework was used to tune the values of the hyperparameters of the testing. The lead times were already mentioned. We defined future windows from 5 to 60 minutes with a 5-minute step between them. And now, let's see the results. We only present performance of the models in terms of selected evaluation metrics, since there are groups of metrics with similar features. If we only focus on the 6 baseline models and not consider the meta models, we can see the following. For 4 or 5 metrics, for instance for POD, the Titan model consistently outperforms all other across all lead times. For the remaining metrics, Titan remains the best performing baseline only for the shorter forecast horizons, for up to 25-35 minutes. Beyond this, for longer lead times, the SPROC nowcasting method becomes the leading baseline, as it is illustrated, for instance, by the FAR metrics. If we compare the 3 L-class variants with the 6 baseline models, we see that most verification metrics indicate that the AI model variants outperform the baseline models. It can be seen on the top or bottom position of the triplets of yellow, orange, red lines, and they are also the least biased ones on the bias plot. Even the first L-class model outperformed the baselines. That was the L-class based on VIL radar product. Subsequently, the further two L-class variants achieved additional to modest improvements. All in all, the best performing AI nowcasting model is the one with the combined inputs of CAPPI and lightning, here denoted by the yellow color. What we see on the triplet of plots here, nothing else than the previous results from a different viewpoint. Here, the best L-class model is declared as the reference, and each baseline model is compared to this reference point. In other words, we visualize the improvements that we obtain if the particular baseline model was replaced by the best performing L-class model. Therefore, the lower the values, the better the performance of the baseline models. Again, we see the dominance of the Titan model indicated by the magenta color, for instance, in the case of POD matrix. Also, what was mentioned before, the fact that the SPROG model, indicated by the dark green color, overtakes the Titan model for the longer lead times. In the case of FAR or in the case of CSI matrix, it can be seen. To assess the quality of our approaches, we also try to compare them with the results of studies that similarly focus on precipitation nowcasting based on optical-flow approaches. These were the E-Titan, Enhanced Titan, and the IVAP approaches. IVAP means that integrating velocity azimuth process. In the plots, they are indicated by black colors. Note that this is only a formal comparison with only displaying the final metric figures borrowed from the corresponding two studies without their direct adoption into our modeling environment or data. Just to put our results in a broader context. The statistics of the E-Titan show that our L-class method outperforms E-Titan in terms of CSI and also for the FAR, while the results for the probability of detection are mixed. On the other hand, the IVAP model shows better performance than L-class variants only for very short forecast horizons, about 15-20 minutes. For longer lead times, our L-class variants dominate. Now, we arrived at the very end of our video, reaching the summary and conclusions. What we constructed. We put together several variants of an AI nowcasting model that uses radar products and meteorological data as input and produce nowcasts of rainfall up to 60 minutes ahead. The core nowcasting architecture consists of two levels. The first level is made of 6 baseline models, which are well-established optical flow approaches in radar-based precipitation nowcasting. The second level of our architecture is a meta-model within an ensemble stacking approach, which has the main role to find the best performing member of these 6 baselines and to construct the resulting nowcast using this top performing baseline. Depending on different inputs, we trained and evaluated 3 variants of our L-class meta-model. The best performance among them was achieved by the configuration based on the CAPPI radar product combined with lightning observations. Furthermore, all L-class variants consistently outperformed the 6 baseline models across most evaluation metrics. This is the end of my presentation. Let me thank you for watching. In the case of any questions, you can reach us at the addresses displayed here. Have a nice day. Goodbye.